Okay, we are looking at statistical inference for specialist maths. And statistical inference is all about drawing conclusions about a population. Now, we can't always identify everything about a population because maybe we don't know what is the some mean or some standard deviation population parameter. And so we have to draw some sample from the population, and then we can form conclusions about that sample. Okay, so let's have a look at some of the key ideas behind this. Alright, so we want to know about the population. Okay, and the main things about the population are what we call the population parameters, and we have a mean and a standard deviation, and those two are the key notations there that we're going to use. And so when we take a randomly selected sample of sample size n, then we have statistics. We've got the mean of the sample and the standard deviation of the sample. They are our statistics. And so when what we're looking at now is that the sample to acquire is going to be numerical data, and that we're looking at. And it's either discrete numerical data or it can be continuous data as well. Okay, so let's consider this as an example. What happens if we're to investigate the questions such as what's the average number of hours spent online by the typical Australian household? Okay, so first thing to realize is, hey, there's 24 million people approximately in Australia. So it's pretty challenging to be able to ask every single one. And when the Australian government try to do so, it doesn't always work out the way it should. Okay, so instead, let's randomly select a sample of people and let's survey them that same question. So let's, as a little example, here's one sample. Okay, now we're looking at hours per week, perhaps, that we might be asking. So this sample has an average about 9.5 hours per week is how many hours spent online. Okay, well, what about if we did that again? If we took another sample of the same amount of people and asked them the exact same question, we might get a different average, maybe an 8.8 hours per week. And so on. We can consider numerous samples. So even a third sample, we did that and we got 10 hours. And so on. And the idea is, what happens if we take lots of samples, many samples, and the sample of people are all the same size, and we work out the average. And so the average being here is recorded and noted down. So if we looked at maybe hundreds or even 1,000 samples of the same size and recorded the average, what do we notice about the mean of the samples? Well, the distribution of the sample mean, we will notice, will be approximately normal. And there's our normal distribution there. So it's important to realize that, because what we have here is we're going to draw on our normal distribution statistics to analyze the distribution of sample means. So when a sample size is large, and that's the key idea here, it has to be a large size. Okay, we have our x bar, which is our sample mean. That is going to be normally distributed, and the mean being the measure of center, which we have here. The mean is the same as the population proportion, the population mean. Okay, so that's our expected value. The mean of our sample means is the same as our population mean. And the standard deviation, in fact, of the sample means is how wide the measure of spread we have in our curve here. The standard deviation is in fact given by this expression, which is this here is the population standard deviation, the population parameter, divided by the square root of n. Square root of n is being our number of participants in the survey, the number of our sample size. So that's important, those two measures there. Alright, so let's consider this scenario. Let's say we've got 300 students studying statistics at a course at the University of Melbourne. Okay, so on a recent exam, the mean score of the exam was 90.5, and with a standard deviation of 10. Alright, so that describes the population parameters for all the 300 students studying statistics at the University of Melbourne. Now, let me pose this question. A sample size of 15 are selected and the means are found. Okay, and then the mean and standard deviation of the distribution of the sample means. What is that? Okay, so first off, we're finding these parameters, the mean of the sample means and the standard deviation of the sample means, of the distribution of sample means. So we find that the mean of the sample means is the same as the population mean. So that is this value here, the 90.5. Okay, whereas the standard deviation of the sample means, it gives by that expression, okay, you identify the standard deviation for the population, which is 10, divided by the square root of the sample size 15, 2.6. Okay, get the idea? Okay. Now, let's consider if the sample size was increased to 30, what effect would this have on the mean and standard deviation of the distribution of sample means? How is that going to change? By increasing the sample size. Okay, first off, let's think about the mean of the distribution of sample means. Well, we will notice that, hey, that's not going to change. It's just still the same as the population mean, 90.5. However, look at the rule for the standard deviation of the sample means. It depends on n, sample size. And so if we increase n, if n goes up, so now the square root of 30, what happens is that standard deviation of the distribution of sample means, that's going to go down. It's going to decrease to 1.8. So that's an important relationship there. They're inversely proportional. The sample size increases and the standard deviation of the sample means is going to decrease. Alright, so let's come back to our main question. So, what is the average number of hours spent online by Australians? Well, if we're going to struggle to ask all 24 million members of the population because, you know, these census things don't really work out the way they're planned, we're not going to know the population and the standard deviation of the population mean and the standard deviation of the population either. So what do we do? Well, in that situation, of course, we can take a survey of a random sample. So here's our sample again, and what we can work out from the sample is the sample mean and a sample standard deviation. And we have these two parameters, these two statistics, I should say. Now, if we don't know what the population parameters are, then the sample statistics, well, they become the best estimates for our population parameters. Okay, we use that as that's all the information we have, so we're going to use that to estimate what the population parameters are going to be. So that's the whole point of the inference, statistical inference, is that we take the sample from the population, we form a hypothesis about what we're interested in, we analyze the statistics of the sample, and then we can form conclusions based on the sample and relate it back to the population. So one such statistical inference we can form are what's called confidence intervals. So confidence intervals allows us to quantify the interval within which the population mean might lie. So if we don't know what this population mean is, if this is unknown, then we're using the sample mean and the sample standard deviation to form a confidence interval. Okay, so it's best to do this when the sample size is large. So when it's sufficiently large, then the sample mean is normally distributed with a mean of mu, which is the population mean, if that is known, and a standard deviation. So that's the basic idea. However, when they're not known, well, we can only use the information that we do have, and it becomes like an approximate estimation. So for our normal distribution, our z-score is given by this expression. So our standard deviation and our mean for the population are unknown, so we're going to use the sample mean and the sample distribution here, the sample standard deviation, S. They become our statistics we're going to use to estimate. Okay, and just by rearranging our z-score, we get this expression, okay, where we can determine x being the value that we're after, the particular limits. We get an upper bound and a lower bound for x, which gives us our confidence interval. So let's consider the confidence interval from the z curve. Well, from our normal distribution, the 1 minus alpha here is what is the population, is the probability that we're forming our confidence interval on. Okay, and then outside this region, we've got what's left over, the tail end, the tail end probabilities. Well, they are a z multiple away, multiple of standard deviations away from the mean, and that's what we were illustrating previously here with our forming our confidence interval. Okay, so let's consider that the blue shaded area, this probability of 1 minus alpha, let's say we're forming our 90% confidence interval. So our 1 minus alpha is 0.9, and then the tails combined, that's this tail and this tail together, will have a total area of 0.05, okay, half of what's left. If the whole lot is 10%, then half of it must be 5%. Alright, so what's the corresponding Z number that matches with this 0.05 probability in the tail, in one of the tails? Well, we can, from our standard normal curve, we've got a mean of 0 and a standard deviation of 1, so we can use on our CAS calculator our inverse norm function. Okay, a very important one to work out our Z score number that we're after. So for a 90% confidence interval, we're getting this value, 1.64. Okay, and you can see on this area over here, the left-hand side, where it's a negative Z value, it is, the area has to be less, is this 5%. Whereas way over on this side, to get the positive Z-score value, we're looking at the equivalent of the whole lot to the left of that number, or that area. So what's left of it is 95%. Okay, and that corresponds to both 1.64, both being the positive and the negative of it. Okay, now that helps us to form our confidence interval. So the confidence interval expression becomes this, where the Z multiplier is this value for the 90% confidence interval, 1.64. Now, let's review in general some of those Z numbers, Z multiple numbers of the standard deviation for different confidence intervals. So if we look at a 95% confidence interval, which is quite a common one, then the 1/2 tail area is just going to be, here we go, 2.5%, and it corresponds to this Z-score number, 1.96. 98% confidence interval is going to give you a z-score number of 2.33, and a 99% confidence interval is as high as 2.58. Okay, so little important table there to remember or to record in your summary notes, and it's a good little thing to look up when you're forming confidence intervals. Alright, let's consider this problem, Mr. Energizer battery. You may not remember this guy. His guy was big on our TV back in the 90s, so, you know, good times. Alright, so let's consider a sample of 40 AA batteries, and they were tested to determine their average lifetime. And it was found that they lasted an average of 2,314 minutes, with a standard deviation of 243 minutes. So let's estimate with 95% confidence the average battery life. Okay, so let's identify some key piece of information there. A sample of 40 gives us a sample size, so n equals 40. And it was found that they lasted an average of 2,014 minutes. Well, there's our sample mean, okay, which our x bar, and standard deviation of 243. Well, that becomes our S, our sample standard deviation. Now, they are our estimating quantitative statistics there that we're going to use to estimate the population parameters. So our 95% confidence interval, where in our single tail area of our curve, we're getting this 0.025 as an area, as our probability. And that corresponds to these z-score numbers. So that can be done on our inverse norm, our function on the CAS calculator. Okay, so we have to calculate the lower bound and the upper bound. So the lower bound is our x bar minus z times, here it is, our sample standard deviation of the sample mean. There it is. And so substitute our values in and calculate, and we get this as our value for our lower bound. And we do the same for our upper bound. It's the x bar plus the z times our standard deviation of the sample mean. And we get that. So putting them together, we can form a statement like so. We can say, therefore, we can be 95% confident that, on average, the battery life of a AA batteries is between 2,238.7 and 2,389.3 minutes. Okay, there's our confidence interval, and the population, the actual population mean for all the AA batteries lies within these lower bound and upper bound. Okay, so here's Mr. Energizer's confidence interval. So from that, some important property in it that we're going to look at. If we take the difference of those two values, we can see that there are a difference of 150.6. Okay, now what we define as the margin of error. Okay, the margin of error is always half the difference between the lower bound and upper bound, and it gives us this value. Now, in terms of the formula, that's equivalent to, here it is, the margin of error, that's equivalent to the z multiple of the standard deviation of the sample mean. So that quantity there is what we define as the margin of error. Alright, so let's consider that idea in a question. What sample size would be needed to reduce the interval to a plus or minus 50 minutes at a 95% confidence interval? So this quantity there, that plus 50 minutes, okay, that is our margin of error. That's this quantity. Okay, so our margin of error of 50 minutes is equivalent to this formula, the z times the standard deviation of the sample mean. The s divided the square root n has to equal to 50. Okay, so our goal here is to substitute in what we have for 95% confidence level, our z-score number, that was the 1.96, and our sample standard deviation S from the problem. And those were those parameters, those statistic values there from the previous question. Okay, so putting them in, and we can do this on a CAS calculator as well, quite easily. We can transpose for n, the sample size, and work out what should the sample size need to be in order to reduce the margin of error down to 50 minutes instead of the 75.3 minutes. And we can see that we have to increase the sample up to about 91 people, 91 batteries in our sample that we're going to be looking at. Okay, so the company Energizer, they've made plenty of claims over the years, but when a company or when advertisements make claims, okay, we can examine those claims in what's called a hypothesis test. Okay, so let's say that we have an advertiser making for batteries making such a claim. You know, it will last for 24 hours of battery life in total. Okay, so a hypothesis test allows you to test claims made about a situation, about a particular result or value that's given to you. And it also allows you to test to see if there's any change or difference made to a situation with a particular intervention, perhaps. So let's define some of the key terms. A hypothesis is what we're calling it's a theory or a premise, usually the claim that someone is investigating, such as we might want to investigate the claim that the Energizer battery is going to last for 24 hours. So from that, there are two versions of the hypothesis. We define something called the null hypothesis, and that describes the currently accepted value for the population parameter. Okay, so that means in terms of the advertisement, the null hypothesis would be referring to the claim made. And then contrary to that, we have what's called the alternative hypothesis. Okay, and that describes the claim that is being tested, the mathematical opposite of the null hypothesis. Okay, so let's illustrate those ideas in our example. So the null hypothesis for the advertisement is that the average life for an Energizer battery is 24 hours. Okay, so we can form our null hypothesis in this way. Our H0 hypothesis is the mean is equal to, which is the population parameter, 24. Okay, so now the alternative hypothesis is the mathematical opposite to this statement. If the mean is equal to 24, then the mathematical opposite will be, perhaps, not equal to 24. Or we can frame that in another way. We could say that it has to be less than 24, which still meets the criteria, that is, not equal to 24. Okay? So an alternative hypothesis could be, this as one example, the average battery life for an Energizer battery is less than 24 hours. Being perhaps our advertisement is an exaggerated claim. Alright, so when we're hypothesis testing, we have our two hypotheses. The null hypothesis, it's where we say the claim that there is no difference between the population mean, or population parameter, so the stated claim. And then the alternative hypothesis, it makes the claim that there is a difference, and the difference could be, we could observe it to be greater than the population parameter, or it could be less than the population parameter. And in that situation where it's greater than or less than as a difference, then that becomes what's called a one-tail test. And when we express it like this, where the mean is just not equal to the population parameter, it's called a two-tailed test because it could go either way. It could go to less than, or it could go greater than. And we're not being specific on which direction we're examining. So the two-tailed test is when the mean is not equal to the population parameter, mean. Okay, we have either to the left or to the right. And there's our sigma again. So the area in the tail is the sigma divide 2, our tolerance significance level, and half of that in that spot. So if you're using a significance level of alpha, a two-tailed test, that's going to allot half of your alpha area, half of your amount, to testing the statistical significance in one direction, and half of your alpha to testing the statistical significance in the other direction, over here. So that means alpha divide 2 is in each of the tails of the distribution for your test statistic. Okay, in both. Now, considering that as a one-tailed test, so if you're using a significance level of alpha, one-tailed test, that's going to allot all of the alpha amount to, or all of the area is going to assign to just one of the tails, to testing the statistical significance in one direction of interest. Could be greater than, or it could be less than. This means that alpha is in one tail of the distribution of your test statistic. When using a one-tailed test, you are testing for the possibility of the relationship in one direction only, that way, and completely disregarding the possibility of the relationship in the other direction. So if you're looking at mean is greater than some value, then you're completely disregarding to the left, which is less than, and vice versa. Alright, so let's consider the situation that's outlined here. Des has decided to increase his mountain bike training by adding an extra 3 one-hour sessions to his weekly training schedule. So he's hoping to improve his best race time. With reference to his race times, let's state a null and alternative hypothesis. Okay, so we've got to think about the scenario and form it and state the hypotheses. So the null hypothesis can be written like so. The extra training does not change his race time from his best race time R. Okay, so the null hypothesis is always about the situation where there is no change to what's described originally. So the intervention of doing extra training causes no change. That's the null hypothesis. Now the alternative hypothesis is maybe the extra training has improved his race time from his best race time R. So it's gotten better. So if you're improving your race time, you're getting to the finish line in a smaller time. So in this case, mean of our average race time that we're going to get after our extra training is going to be less than his previous best race time. And that gives an improvement. Get the idea? So in this case, this is a one-tailed t-test, a one-tailed hypothesis test that can be done. So the significance level that we choose for our test, which I'll explain more in detail very shortly, our alpha, is all going to be allotted to just one tail only. The whole amount is dedicated to here. And that's going to correspond to a test statistic, a z-score. Alright, now when we are doing these hypotheses tests, there's a kind of a procedure or approach we'd like to take. So before we do the analysis, we're always going to make the assumption first that the null hypothesis is true. So that's our thinking that we adopt when we go into a hypothesis test. We start by thinking that, yep, on the assumption that the null hypothesis is true, then if there is sufficient evidence to say so otherwise, I'm accepting that that is the case. So the next step is we take a sample, we take some measurements from the sample of a certain size, we look at the sample mean and the sample standard deviation, and we calculate a test statistic. And then after that analysis, if there is sufficient evidence to say, then we may choose to reject the null hypothesis and believe that the alternative hypothesis is true. Okay? Or this is the alternative approach. Now, be mindful that we never go about proving the null hypothesis, because we've already made that assumption. It's based on the assumption that the null hypothesis is true in the beginning. So we don't prove that the null hypothesis. We just go about, we can accept that it is true unless we have evidence to say otherwise. Okay? And we can then reject. We can reject that null hypothesis if we do have sufficient evidence to say so. Now, when we make decisions on whether we choose to reject the null hypothesis or whether we accept our assumption that the null hypothesis is true, in making those decisions, there's two possible errors that can occur. So these errors are categorized in two ways. They're called a type 1 error and a type 2 error. So the type 1 error is defined in this way. So when the researcher rejects the null hypothesis, maybe he from his statistical test, he got enough evidence perhaps for him to conclude, hey, I can reject the null hypothesis and accept the alternative hypothesis to be true. Well, if he goes about doing that when the null hypothesis is actually true and the statistics weren't able to demonstrate that, then that's the situation of a type 1 error. Okay? So the probability of committing a type 1 error, that is defined as the significance level. It's our alpha amount. Okay? So we start a hypothesis test by defining our alpha amount. This is our level of risk we're willing to take in committing a type 1 error. Okay? Whereas the type 2 error, well, that occurs when the researcher fails to reject the null hypothesis when it is in fact false. Okay? Implying that the alternative hypothesis is true. Alright, so let's consider those two scenarios. So this is describing the true state of nature. This is the actual factual case. The null hypothesis could be true or it could be false. So from our statistics, drawing our sample, we can form two conclusions. We can either accept the null hypothesis or we reject it. Now, from that we get these four scenarios. So if the hypothesis is true by nature and we've accepted it we've formed that conclusion that yes, then that's a good conclusion. And alternatively, if the true by nature, the null hypothesis is actually false, and we've formed the conclusion to reject that hypothesis from our hypothesis test statistics, then that's also a good conclusion. Okay? Now, the alternative, if we do either of the other two scenarios, that's our type 1 error and our type 2 error, rejecting a true hypothesis or accepting a false hypothesis. Okay, and the probability of rejecting a true hypothesis is this sigma, is our significance level. Okay? Whereas the complement of that, 1 minus sigma, is the probability of forming that good conclusion there of rejecting the hypothesis when it is indeed false. And that's equivalent to our level of confidence when we're forming a confidence interval. Okay, get the idea? So this is a nice little summary diagram of the different logical conclusions there. Okay, let's consider this problem. The probability of low birth weight in Australia is about 6%. So that's our stated knowledge, that's our population parameter. So out of 200 babies born at Bundaberg in Queensland during a period when aerial spraying of sugar canes was common, perhaps a couple of decades ago, not so far. In that period, from that survey of 200 babies, 18 of them was observed to have low birth weight. Okay, so the local paper claimed that this proves that the aerial spraying was dangerous because the rate of birth problems was about 150% greater than the national average of our 6% for low birth rates. Okay. Now, the aerial spraying will only be stopped if there is sufficient evidence to do so. All right. So, from that survey, will that give us enough evidence? Well, let's consider the two hypotheses. The null hypothesis is the aerial spraying is safe, as the low birth weight proportion is unchanged. So it's always the way we structure our null hypotheses, unchanged from what's stated. Whereas the alternative hypothesis is that the aerial spraying is dangerous, as the low birth weight proportion is increased. Okay, so you've got a higher proportion of low birth weights occurring in the population, which is not a good thing. Okay, and so if that's due to aerial spraying, then it's considered dangerous. And in that case, well, they're likely to stop that practice, that agricultural practice. Okay, so let's just say if a type 1 error has been made, well, what does that mean? What conclusion was reached? Type 1 error. Well, rejecting a false hypothesis. If they've rejected a false hypothesis, then the aerial spraying is not safe. Okay? Whereas if a type 2 error has been made, what does that mean? Well, what conclusion was reached? Okay, so failing to reject the null hypothesis, when in fact it is true. Well, in that case, there is insufficient evidence to conclude that the aerial spraying is safe. Alright. So, being able to recognize type 1 and type 2 error and drawing on a table in this way is very useful to remind you what is the definition of a type 1 error and what's the definition of a type 2 error. Okay, so we're going to now examine our hypotheses testing, okay, but I think we'll better save that for a next video.